Back in 2017, a paper dropped from some researchers at Google, and it had this deceptively simple title. Little did anyone know that paper was about to completely change, well, everything in the world of artificial intelligence. Today, we're going to break that paper down. Attention is all you need. So let me ask you something. Did you ever notice that right around 2017, tools like Google Translate just suddenly got really good? Like uncannily good? Well, that wasn't magic. It was this fundamental breakthrough that solved a massive problem at the very core of machine learning. So, what was the problem? The paper calls it the fundamental constraint of sequential computation. Let's just call it what it is, a sequential bottleneck. And to really get why the solution was so brilliant, we first have to understand the old, kind of clunky way AI used to deal with language. See, before this paper, the state-of-the-art models were these things called recurrent neural networks, or RNNs. And they basically worked a lot like you and I read a sentence. They'd process the first word, then the second, then the third, all in this strict, unchangeable order. The whole time, they're trying to hold the meaning of the previous words in memory as they move along. Now, this one-word-at-a-time approach had some huge flaws. I mean, first off, it's incredibly slow. And with long sentences, the model would often forget what the beginning of the sentence was even about by the time it got to the end. And the worst part, you couldn't just throw more computers at it to speed things up, because every single word depended on the one that came right before it. It was like having an assembly line with just one poor worker trying to do every single job in order. The whole field was just stuck on this one-by-one method. But then, the authors of this paper asked a totally revolutionary question. What if we don't have to do it that way? What if a model could look at all the words in a sentence at the exact same time? And their answer to that question was a brand new mechanism, one that would become the absolute foundation of their model. It was a totally new way for a machine to pay attention to language. They called it self-attention. Basically, it's a method that lets a model weigh the importance of every word in a sentence against every other word all at once. So it can instantly see how king relates to he or how queen relates to she across a whole paragraph without having to read it word by word. This completely did away with that whole sequential process. And this is the architecture they came up with. It's called the transformer. Yeah, it looks a little complex, I know, but the absolute key is right here in these blocks labeled multi-head attention. Think of this as the engine room. This is where that self-attention mechanism lives, and it's what lets the model look at the sentence from a bunch of different angles all at the same time. It's the magic that makes it all work. So how does this attention thing actually break that sequential bottleneck we talked about? Well, the key is that it allows for just massive parallelization. Let's try a simple analogy to make sense of it. Okay, imagine a team of specialists. Instead of that one worker going down the line, you give every single word in the sentence its own expert. Then, and this is the cool part, you let all of those specialists talk to each other at the exact same time. The specialist for the word it can instantly shout out to every other specialist, hey, who are you guys talking about? The context gets built not in a slow plotting line, but in one single, massive, parallel conversation. Instantly. And here's the technical payoff right from the paper. With the old models, the longer your sentence, the more steps you needed. Simple as that. But with self-attention, it's always just one step. It doesn't matter how long the sentence is. The path for information to travel between any two words is always direct, which makes learning those long-range connections so much easier. Okay, so the theory is really elegant. It sounds great on paper. But did it actually work? Well, the results weren't just good. They were absolutely stunning. First, a super quick primer. In the world of machine translation, quality is measured with something called a BLEU score. All you really need to know is that it compares a machine's translation to a bunch of high-quality human translations. The closer the match, the higher the score. Pretty simple. So on the standard English to German translation task, the very best models they had before, even when they ganged up a few of them together in what's called an ensemble, they topped out at a BLEU score of 26.3. The new transformer model, it just blew right past that, hitting a score of 28.4, a whole new level. But wait, here's the real kicker. The transformer wasn't just better. It was ridiculously more efficient. It got that new state-of-the-art result using less than 1/10 of the computational power it took to train the old models. So it was better, faster, and cheaper all at the same time. That's the holy grail.
Now, a jump of over 2.0 BLU points, that might not sound like a lot to you and me, but trust me, in the world of machine translation, that is a massive leap forward. It's at a new state of the art, and it just completely changed the game overnight.
And the impact? Well, it went so far beyond just making translation a little bit better. What this paper really did was lay a brand new foundation for the entire field of AI. Think about it. This transformer architecture, this whole idea of parallel self-attention, is the T in GPT. It's the fundamental building block behind pretty much every large language model and generative AI tool that we're all using today. And it all started right here, with a paper that was just trying to solve a problem in translation. And what's just wild is that the authors, they seemed to know what they had on their hands. They end their paper with this line: "We are excited about the future of attention-based models and plan to apply them to other tasks." I mean, talk about an understatement, right? That is such a beautifully low-key way of saying they knew they had just unlocked an entirely new era of possibilities. And this kind of brings us to a final thought. For decades, the entire field just assumed that processing language had to be sequential, because that's how we experience it. By questioning that one single core assumption, they solve the whole problem. And it really makes you wonder, doesn't it? What other impossible breakthroughs are just sitting out there waiting for us, if only we're willing to rethink the one thing that everyone else just takes for granted?